Hello, and here we are again with Physics for the 21st Century. Again, my name is Greg Perugini, and today's topic is Introduction to Fluid Dynamics. Now, this is just going to be an introduction. We're going to cover in two subsequent topics a little bit more in detail in examples of fluid dynamics. But right now, we're going to just cover some very basic stuff, some very basic problems. There should be no issue for you guys at all. Just the same old drill, so to speak. So what we have is that fluids obey Newton's law. Gravity affects them, of course. They are affected by pressure. Certain, as we saw in last topic, certain substances obey stress and strain differently than others, and fluid is no different. Of course, fluid cannot shear and fluid cannot stretch, but fluid responds to pressure. So fluid's density and viscosity affect its flow rate. So we use a Greek rho for density, and you probably have seen this already. And the measure of density is mass divided by volume. It's mass per unit of volume. Kilograms per meter cubed. Now that's different from pressure, and this confuses some students sometimes because we're using something that looks like a P in both cases. If you remember, pressure is force for a given area, which is newtons per meter squared. Now we're going to measure pressure in something called pascals, which is a unit of Newton per meter squared. Now, 1 atmosphere is sort of a handy measurement, 1 ATM, as you see it on the screen there. Typically, it's written 1.013 times 10 to the 5th times 10 to the 5th pascals. So, how do we apply these? Well, pressure, we're feeling this all around us equally, and there is an atmosphere pressure on you, give or take, depending on whether you're at sea level or not. And an atmosphere, as I said, is 1.013 times 10 to the 5th pascals is 1 atmosphere. And so when we want to know the absolute pressure, we have to add to that pressure of 1 atmosphere. We have to add to that something called gauge pressure. This is the gauge pressure. It is the addition or subtraction from absolute pressure, and that depends upon the variables you see here. The density of the material, and again, density is mass per volume. Gravity, and on Earth we're going to use 9.8. And the height, or in this case, depth, would be a positive number, right? If we're going down into an ocean, for instance, underwater, so in an ocean, we would talk about seawater, right? Which would have its own density, 9.8, and how deep we went would be y. If we were going up in a balloon, though, the depth would be a negative number that we would be subtracting from the atmosphere. So our pressure that we would feel, this pressure that we would feel, would be less than 1 atmosphere because this would be a subtraction. So that's gauge pressure in a nutshell, and absolute pressure, this being absolute pressure. So if asked for absolute pressure, this is the number we're looking for, adding in an atmosphere. What we would read on our gauge already has atmospheric pressure built in, This is gauge pressure. Density of whatever it is, air, water, whatever that's being acted with, 9.8 times the height or depth. Now the flow rate through a material is conserved if I'm flowing material. This is another topic here. If I'm flowing a material through, a flow rate is velocity times a given area. Like if I'm flowing through a tube, let's say I'm going through a tube, it's round at one end and square at the other, the flow rate in is based on this cross-sectional area, pi r squared, right? That cross-sectional area. Here, obviously, it's width times height, since it's square. But it's conserved in the sense that the flow rate in must equal the flow rate out. And you've known this also when you have a hose, right? If you have a hose and you have a nozzle on it, if you close the nozzle, make it a smaller opening at the bottom, what happens, right? You get a faster velocity out. So the flow rate, and this is called the equation of continuity, is conserved. So those are the topics I want you to know for this particular assessment. Not too bad, right? Should be fairly straightforward. You have to have your densities for particular materials on hand. Obviously, a density, when we're talking about a density of water, is going to change if it's seawater, and that's going to be different density for oil, for instance, or whatever the material might be, mercury or whatever it might be. So have that on hand. Practice these, because we're going to do some complex applications and topics to follow. We're going to do Bernoulli's equation. We're going to also do some work with Archimedes' law. So that's all you have for this particular topic. Good luck.